So, so today's video is on the asymmetric symmetric drone delivery system for NSIGII. So NSIGII, N for November, S for Sarah, I for Indigo, G for Gold, G for Gold, I for India, I for India. So basically, it's only one G. N is November, S for Sarah, I for Indigo, G for Gold, I for India, I for India. Is human rights protocol. This is on the drone delivery system for food, water, and shelter. But NSIGII sues people, then uses the drone system to deliver food, because suing people is what the system does. So here's the bank account, and when you sue someone, you just can have food, water, and shelter, because the human system is perfect. So people will stop touching you. People will stop touching you. When people stop touching you, you use that money to sue them through a court process. But NSIGII is literally on the drone system. Now, I will be showing you some things here, guys. If you're interested, if you're watching my channel. This here is a triangle-based prism, a triangle-based pyramid. A triangle-based pyramid. It has three sides. The three sides are, no, it has one, two, three. One, two, three. Four sides. Four sides. These four sides are four surfaces of a face, and this represents reflection of a message. For example, a message is encapsulated into this prism, and this prism is a triangle-based pyramid where the messages reflect each other. So you have the three messages reflect over the axes of the system. So you have the message, you have four messages in total you're sending, or four sets of Hamming code. Four sets of Hamming code via rotation and reflection, or rotative symmetry, reflective symmetry, enlargement and rotation. To prove this reflection has been proven in this theorem. So you have to understand that this is a Hamming code process, and it's basically the first video on the first model of the NSIGII protocol. This should give you a strong foundation if you still continue my channel. Let me show what I'm saying. So let me lay down the alphabet on the system here. Let me lay down the English alphabet and give it all indexes. A, B, C, D, E, F, G, H. A, B, C, D, E, F, G, H. I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So, for example, you have a set of Hamming codes via a Manhattan distance, and a Manhattan distance via the Hamming code. So you get the Hamming code and you get the Hamming distance, which can be by the Hamming code. But I come to computer, so I should remember how I computed it. So message A to message A is 0. Has the code 0, 0, and number 26 has the code 26. So A has 00, B has 01, C has 02, D has 03, 04, 05, 06, 07, 08, 09, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. Z is 25. I'm trying to demonstrate that this image here this system can be integrated over. So my first hypothesis is to define a trident graph, an asymmetric symmetric trident graph of the images. For example, the message "Hello world" can be encoded into the system. Hello OBNexus is defined as 07 04 11 11 11 11 E04. So the message hello is 07 04 11 11 OB 14. Oh, so they have hello OBNexus will be O14 B B01 I will be 08 N will be 13 E will be 04 X will be 23 U will be 20 and S will be 18 from 0. So the codec system is basically a path system. What this means is you cannot allocate more than the system. So you have two main operations. You have exclusive or you have a shift pad, a pad shift, a pipe shift. Via the honeycomb model. This is computing on a lattice which is asymmetric, meaning that there's no symmetry in the message. You send a canonical message, uniform no a canonical message, and can be tampered over a signal frequency, whether digital or analog, to be changed because the message cannot be changed because there's no codec. If you try to recompute something through the message, and symmetric means the message can be mirrored. Asymmetric, symmetric. So the message is asymmetric, symmetric. What this really means is when you get a message like "Hello OBNexus," you have some kind of uniform normalization. Canonical signature that the message holds. So first things first, let's start with the message now. Now, the message is a magnetic memory system. So the magnetic memory system is inside the packet, and this is basically the packet, the mirror packet. For example, if I send this message over a channel I have a half to send. I have half message sent, half received, half sent, half received. This works beautifully because the message is magnetic. It's basically a fault tolerance system, a visiting fault tolerance via visiting fault tolerance via a Hamming code, via a Hamming encoding or Hamming distance on a lattice. So how does this work in practice? So if I send hello OBNXS, I'm sending the binary equivalent of 07 if the codec is only from limited alphabet with A to Z. A to Z. If the input is A to Z, A to Z only. Now A to Z has the polar opposites. So it can be encoded via inverse left ending. So you have 40 encoded here. The four type of encoding used determine are the reflected surfaces of the message. For example, you get left endians A to Z, left endians, right endiness A to Z. Now you have left endiness Z to A and right endianness Z to A. These are the four axes of symmetry that the message remains isomorphic and can still be coherent. Therefore, you have a message of hello open access via encoding of a pipe right shift and or right shift a pipe left shift. For example, the message hello open access will be 07, the binary number 7. And that binary number 7 will be, let me get my laptop. The binary number for 7 will be programmer decimal 7 0111 for H. Zero, so you get 0111 for H. The decimal number 4 0100 11 or 11 will be the binary 1011. The decimal number 14 will be O will be 1110 and O will be 1110 and B will be 01 01 will be 0001 and N will be 13. 13 will be N, that will be 1101. E will be 0100. X, U, and S. U, X is 23. X is 23. X is 0001 0000111. U is that'll be 0001 0111. U will be U will be 20. 20 will be 0001 0100. S will be 18. 18. Decimal number 18 will be 0001 0010. And this means hello OB Nexus. So if you look at my notes, guys, I have the messages here. And as you can see, there's a codec already. So this is a table of alphabets, and they're four-sided. You have the mirrors of the asymmetric mapping. So the message knows itself via symmetry, but the message has a codec to do it, and that's what the NSIGII is encoding. The message is basically have a rotation and a reflection. This is basically a prism that is trident. So it has four sides to the message. No matter how you rotate it, there's four axes of symmetry, and the message has a reflexive opposite, a polar opposite. Two, which is the conjugate model of the message. So when the drone delivers food, water, and shelter, and there's a message, it's tracking you in real time, and the drone is tracking you based on your coordination. Your laptop, you're holding your laptop, and it's tracking you. You can be holding a signal to you via auxiliary components. So this is instantaneous algorithm via a graph. What's next? So what's next, guys? So this is the first model of the system. This is basically on this one here. Can you see it? Oh, can't see. Can't see. This is basically on this diagram. We're going to trapeze model. So the message is magnetic too. It's not magnetic in the sense that it's magnetic. It's magnetic, but it's basically for based on the drift theorem. So let's solve for this message first. We'll go to the drift theorem. So to solve, what I'm trying to solve now is the allocation system of the message. Because the drone flies, but once the message is sent, the drone basically once the message is sent to the drone picks up the food and comes straight to the user, wherever the user is. That's the goal. So you got the drift theorem here too. So that's the goal. So you have a drone anywhere in the world, and the drone delivers the food to the person as the person is moving away from the drone. So that's the goal. So for example, you have the drift theorem. The drift theorem defined as a color coding system via a three-way bipartite color graph. In this framework, this would mean there's a discriminant b squared minus 4ac. Let me just do it again, because I will not really for this. So let's allocate the message. So the left in this model will mean that you start putting zeros from the right, but the mirror opposite will be the having something from the left. So so you're gonna have the mirror be left to right, which is basically the NDS conjugate model, and this is a mirror opposite of the NDS model. So you're gonna have so if my message reflection system. So how the message when the message gets sent, you get a reflection of the message on the side. So you get the receiver be a side flip. But when you flip twice the message, so basically, so basically, this model is related to some other model here. Some model of happy business. So let me draw the other model. So the model here, let me get to the 6. 26 is basically um, 26. Basically, number 26 is 25. Sorry, 25. And 25 is 0, 0, 0, 1, 1, 0, 0, 1. 25. So, so I'm just sending this message over. So if I send this message, I have to have two models. So this is the first model. So this message is a polar message. Because once you send a message, my drone has to start coming. And my drone knows it's drifting away from me. This is the second model. So this model ensures the message is tied to the user's location, like a GPS system. So you have a GPS model of the message here. So what does this mean in practice? So you have the message sent. The message sent in a half sent, half received. But you're gonna have a spring. Now the spring has a payload, which is the message itself. Now the spring being pulled down by some weight. It has an auxiliary movement in the drift. So let's talk about the drift theorem first before we get to this model. But the drift was really put to start message. So this message is sent. It will have to land on the plane. So if you have the compute the pipe, the message packet, compute the trident packet. So the trident packet model, so I'll speak about that. So the trident packet model means there's three messages that are basically force storage. You send three messages together, and you get three packets, only one. But this is one packet. This is a trident packet. But one is basically force storage. So you can have these three working on having lattice. For example, you have the 07, 04, 07. They lie somewhere on the symmetric lattice. And you want to ensure that you can index everything before you send it. So you're gonna compute the trident packet number. These three packets are a set of a packet of encoding via yes, no, and maybe via consensual coding. But the oscillator springs. So for example, you have coherence via the three trident packets. So trident packets are one of the events. So you have three checksums. Basically by video sim. So basically, what's my pen? So you're gonna have a ruler, draw this again. Centimeter. So you're gonna have my hand distance. So let's do some writing here. So you have how many? 1, 2, 3, 4, 5, 6, 7, 8. No, you have 1, 2, 3, 4, 5, 6, 7, 8. So you have the 8 bits in this model where 25 Z is equal to 25 index, and the binary number is 0001 1001, which is number 25. Now, 25 can be minus 25, minus on the scale, or positive on the scale, or positive on the scale, and positive minus on the scale, positive here. Because it's basically flipped. So this model here, and the Hamming code lies in this like this. So you're gonna have the things that are positive. Basically, positive means left engine down, starts on the left, and the left will be a lattice, left to right. So you have positive or right, left to right, L to R, and R to L, R to L, R to L. So you're gonna have the message flying the lattice. And the lattice is basically heterogeneous homogeneous. So you're gonna have the message. For example, if you have the Hamming code, where is what to put this? Should I do a full grid? No, so should I don't know what to do here, but I do know what to do. So you have 0001. You have 0000, which is A. If you have A, you have the opposite of A, which is basically Z to A. So the line, so you're gonna have H here. So H is basically, I'm looking for the smallest number here. H will be A B C D 07, but no, that will be E. So E will be E. Oh no, this will be B. B will be priority 1 B. B will be priority. So B will be left. B will be 0000001. This will be 00000001. B will be B will be this is the middle here. A to Z, that will be the middle of A to Z, which will be 25. How many letters are there? 1 to 26 divided by 2. 26 divided by 2 is what? 26 divided by 2 is 13. 13 will be N. This will be N. And N will be in the middle of left and right poles of the system. So you're gonna have two poles, two polar opposite poles, and N will be N is computed as how many? What's the units of N? 13. That will be 1. 0 1 0 0 0 0 1 1 0 1. N. So N will be 0 0 0 0 1 1 1 1, and L will be 13. N is number 13. Index number 13. Because of the model, you have to ensure that it's translation. So N will be N on the left engineer's pole will be 0. Basically, I have to get an encoding table here. So you have left over. So basically, the left will be 0 1 0 0 0 0, and then the right will be 1. No, left will be 0 0 0 0. And 0 0 0 0 0 will be matrix of 0 0, because that will be the 4 zeros in a system, in a binary system, the 4 zeros. And I'm showing the model said right will be left to right. So that will be L that will be 0 0 0 0.
And the right one will be a right index of A. Let's say A. Could be 1 0. No, it would be 0 0 0 0. 1 0 0 0 0 0 0 0 1 1 0 1. And you have the inverse. To flip it, you have to have the minus one. So you're gonna have to the power of the negative one. We're gonna have n. So basically, you're gonna have the inverse of n. So I can't put it this. So n is 0000 1100, and you have three set of bytes. So you have m, but that's n is basically left to right, LTL. So give n LTL. We have RTL. Basically, you have right to left. Basically, right to right to which would be the polar opposite of m, and that will be 1011 0000, which is basically n, but right NDS to left NDS, you know. But you have the inverse of the system. So everything has an opposite of left to right NDS, two, based on the rotation on your computer. So this will resolve the priority signal, the priority byte over the model. But the first goal is to define how this works alphabetically. So you're gonna have a message. So the message will have left to right, right to left, and the inverse model, conjugate model. Example. So you have 0111, which would be 1110, 0010 E. Basically, so you're gonna have the conjugate, and you have the conjugate, and the conjugate will be conjugate or RTL or conjugate or get the RTL left to right, and you have the conjugate left to right, which is basically the conjugate model of the system, which is the fractional equivalent of the system. So you're gonna have conjugate row get L to right left to right. So you have left to right. You're gonna have 1101, 1101, 0111, 0111, 1000, 1101, 1011, 0010, and you're gonna have X this one. You're gonna have 1110 1000, 0010, 1000, 0100, 1000. I can have the module there. So basically, I'm just giving me myself the formula to do this. But now basically now the rule for beginner the competition beginner. So the message has to be now sent, but if it's half sent, so it will be over a period of 2 pi, which is a period of 2 pi, which is 2 pi is a period. But so you're gonna have the oscillation. So you're gonna have the first step. So the first step is the transmission model. The second step is the spring signal model, the spring drift. And the for it to be sent, this is the spring drift. It's set, it locks into the target, it locks into your computer, and that's basically the answer, the negative pi r squared, the negative pi 2 pi, for one period, which is one period, and you get a negative 2 pi again for two periods for vacations. You get negative 4 pi. And negative 4 pi is the period of the oscillation of the spring over cosine, over cosine. So on, over cosine. And the cosine represents the force times displacement times cosine, which is basically force times displacement times cosine. So force times displacement times cosine is work in a system. But you gotta calculate the work done on the spring. So the message is sent, but the message is like a magnetic message, because the drift is defined in this framework of angular momentum too. So I'll come to that later. So I think we'll continue on the video because this video is going on so far. So basically, I'm saying that we have left to right, right to left, right endiness, and then you get the inverse of the message. So you can start from 0, 0, 0, 0, 0, 0, 0, 0 as z as number 1, and as index 1 from z to the 5. But the message has to be sent over the period of 2 pi or negative 2 pi, because 2 pi in one system is negative 2 pi in one system. And that obviously you have to hold negative. So you hold, but you never lose. So the system measures this magnetic position. If you hold the message, you already have the message. The mirror opposite shows this how can happen. So you have a system of pipes. So the next step is to compute the mask, the bit mask, and the right shift of the message over the alphabet. Over the alphabet. So this will work by this. So let me get my calculator out. So you have the bit mask. So how this works, the bit mask will work like this. So the bit mask will work like standard bit mask. You're gonna have a binary system. No. Logo shift. So you're gonna have a pipe. So you're gonna have the message. So if I write the full message, it will be like a string of bytes, but the message will be hello world. So that will be the decimal number 7 14 11 11 14 7 7. So 7 bytes will be left shifted, will be stored, will be realigned. Basically, will rotate. Basically, when you rotate by half, that's the rotation cent. So the rotation basically a half cent will be rotation of the lattice. So basically, the lattice represents the geometric space of root space 3. So what that means is you have the message before it's sent facing you. You're looking at the message, but when you rotate the axis minus towards you, if you rotate the axis towards you, that means the message is already half sent. So the last will be the message computer over. So you're gonna have the code you want to do this. So for example, if I then rotate this by minus a half, minus a half. So for example, the geometry says so, minus a half, and minus a half will be I can't do this. So what am I going to do? What's the formula? So the formula will be to a half. So you get a half, which is facing you, and you get minus a half, which is facing the other way. And minus a half means you are sending a message. You don't want to hold it anymore. So basically, you want to hold state of the sources. So and when you then send a message, it then aligns to you, and then you send a message because you want to get the message. But there's 3 standards to this. So you're gonna have the symmetry reflex. So the image already there. So yeah. So basically that is basically a computational space, and that space is in R3 space. So that's going to represent the geometric asymmetric symmetric drone delivery system that's just tracking you in real time via the drift theorem. So the drift theorem again is defined as dt equals to pt minus ct, where p is the projected point, d is the drift itself, c is the camera projected point from p, from the projected point of p, and you get 1 minus t times c plus t times p, where t and p are the no, 1 minus c times t plus times t times p. No, times. So the times will be times the time. Basically, this is basically the weighted average of 2 points, and you get 2/3 t, 2/3 p, plus 1/3 c, which represents the geometric equivalent of the lattice. So you can have 2/3 of the mirror, two measures to the same, plus 1/3 or plus 1/3 of c, which comes to the projected point of c, which is the line of the lattice. So this is gonna stop now because I haven't got it right, but I've got it right. So, but it's coherent. So I'll just be mapping out the system. So the coordinate system is meant to ensure that the spring oscillates up and down in real time, so it can really be tracking the person like a GPS system whenever it's really sent. Because if the message is the payload and the spring doesn't operate all the time, you have to send the message in real time, and it's a tracking system of where someone is going as they move around across the domain. Business is single protocol for giving what doesn't matter where a person is going. If a drone, if I cannot find my two computers, I'm gonna buy a Chromebook to prove this by worth. If I cannot find two computers on a network, then this has failed me. So I'm gonna buy another computer to do this basically. But this should work. So again, remember that it works in theory and practice, guys. So, because I've already sent the message here. It's not like a mercury system. It's gonna be like half sent, half collapsed. But it does work. It does work. It's just that it has to implode. It's not imploding. It's not exploding. It's just the message is coherent enough to be symmetrical access. So this is calculus 1, 2, and 3. I'm studying to do it, guys. So you have to see. So what's next in my next video? In my next video, so this is spring here. The spring is operating on a dam, and it's measuring drift. And the drift is basically something moving away from you, something moving at an angle away from you, or something moving like an opposite angle away from you, or moving on the other side. You're not moving, and something moving at an angle like 45 degrees or 35 degrees at an angle away from you, not 90 degrees angle. So you got that drift away. But the oscillation of the system is measuring the drift of you moving away via basically it's an auxiliary observer. So this basically think of the drone as this spring, and the drone is computing this drift, the drift of the system moving away from you. And the drift theorem allows you to you estimate with great precision via a GPS coordinate system of the lattice. So you can give you field research. Like me trying to find you. This is me and you play Marco and Polo, but I'm flying ahead of you. I'm flying. I don't really know where you are via a half measurement, a quarter, and an eighth measurement based on the conjugate model or system. Basically, the conjugate model represents the model of calculation of a negative space, and that's what the conjugate model. So the conjugate model is like 1/8, 1/2, 1/4, 1/6, and 1/8. And that's what you don't have to hold a negative fraction. You do it in that system, but that's what's computed with the conjugate model of binary systems. And that's what's going to do the conjugate model. Anything else, Namdi? No.